empezando 15 minutos tarde, nos moveremos por 15 minutos. Tenemos al doctor Kee Yuen de la Universidad de British Columbia, en Canadá. Nos va a hablar de resolución de ecuaciones y las variedades proyectivas de Stiefel, una mirada breve al legado matemático de Samuel Gitler. La conferencia será en inglés.
Even though it's been many months and my dear friend Samuel Gitler passed away, today we're standing here and being in Mexico, participating in this event, I still feel a great sense of loss. I have lost a very good friend. I have lost a great source of inspiration in terms of mathematics. I have lost a great source of warmth in terms of friendship. I have lost a lot of meaningful interaction possibility in terms of humanity. I shall always remember my very good friend, Sam Gitler. For the purpose, I would like today to just pick up a very tiny corner of Sam's work, which is tremendous and voluminous and very diversified, but I will pick just a little corner, one of his results. And I would like to go through the way he arrived at this particular paper of his and share with you my understanding of that paper. Even though that is only a very small corner of his work, it already gave me a lot of inspiration in topology and in my own research. So let me begin by going back to some very basic things, namely equation solving. Well, suppose very simply we have that system of homogeneous linear equations, and it can be written in matrix form with the coefficients put in a matrix of rows and columns. And this is the data now. The number of unknowns is m. They are called x1 up to xm, and there are n equations, as you can see on the top. The whole system is the system star, and there is the coefficient matrix that I call capital A. Think of all these coefficients to be real numbers for the purpose of today's talk. But you can also think of it as more general numbers. All right, and well, try to solve this equation. Obviously, there is the trivial solution, x1 equals 0, x2 equals 0, and all x's are known equal to 0. That certainly satisfies the equation system. We call this the trivial solution. But now I give everybody an invitation. A blank is provided there, and in the blank, please write down some numerical conditions on n and m, on the number of unknowns and on the number of equations. So write down a condition that will guarantee that the system you have will also admit non-trivial solutions, other than all the variables unknowns x being 0. So write down a numerical condition on the blank and try to make the guarantee. Anybody who has gone through even high school algebra or college algebra will be able to do that, and here it is. M bigger than n. Then you write down the requirement that the number of unknowns be more exceeds the number of equations. All right, and then everybody knows that under this guarantee of numerical conditions, you can certainly find non-trivial solutions to the system. And the argument is very intuitive. You have m variables, x1 up to xm. For each variable, you have 1 degree of freedom to choose a real value for it. So you have a total of m degrees of freedom. But there are only n equations, so you have imposed on these numbers n restrictions or constraints. When your degree of freedom exceeds your number of constraints, you can exercise your degree of freedom, choose some of the x's to be non-zero, and then go ahead to find the other x's. And that will have a solution for you when some of the x's are chosen to be non-zero. So this is a very simple method. Anybody can answer that. And this is only, of course, 18th or 19th century mathematics. Nothing special about it. However, it does lead to one modern terminology that is useful. So, if a system of linear equations is like what we have, and if non-trivial solutions can be found to that system, we call this situation by saying that this system, or by saying that the coefficient matrix A equal to Aij has linearly independent columns, or simply that this matrix A is column independent. And that is a term only perhaps presented in the 20th century. Now, let us go to an analogous situation. We'll talk about other systems of equations, and here they are. This time, I will not be dealing with linear equations. I will be dealing with homogeneous, simultaneous, bilinear equations. So, I have a system of equations now. This is called SHARP, system SHARP. And there are n equations again. The left side of the equations are bilinear forms, and the unknowns are total r plus s in number. They are separated into two sets. First of them, x1 up to xr are called x's, and the remaining y1 up to ys are called y's. And there are n equations, and you indicate them by subscripts. I running from 1 to r, xi's, yj's, j running from 1 to s, and then equation number 1 up to number n, k equations 1 to n. All right. Now, let us contemplate the same system of equations exactly in the way as we contemplated before. All right. Well, there are obviously some trivial solutions. If I set all the x equal to 0 and give y any value, then of course all the equations are satisfied. That would be a solution that is trivial. On the other hand, if I set all the y's equal to 0 and all the x giving them arbitrary values, that would be a solution too. Anybody can see that, and it's very trivial, so we call it trivial solution too. Then the invitation comes just like before. I will provide a plan for everybody. Inside this plan, try to write down some numerical conditions on R, the number of x unknowns, and on S, the number of y unknowns, and on N, the number of equations. Give me some numerical conditions, write them down on the back, so that these numerical conditions will guarantee that in addition to those trivial solutions that everybody sees, there will be some non-trivial solutions. In this context, the non-trivial solution will mean that some of the x values won't be 0, and some of the y values won't be 0, and yet these values satisfy all the equations. So here is then so to speak, an invitation, and I am always soliciting response from the mathematical community. The reason is that this question is, up to the present moment, is still an open problem. It is still an open problem. The only partial results are known. Some people would provide some response, but there may be other responses too, and nobody has gotten a complete picture of this particular situation. It just deals with equation solving, very simple. Some of them might even see the connection to Santiago's law. There are some quadratic things of quadratic nature in there. All right. let's try to look at that. Well, we had our experience. So how about just do something like before? We learned from the linear chase that we can get good numerical guarantee by imagining that the number of unknowns be exceeding the number of equations. In the current case of the system, the number of unknowns is r plus s, the x's plus the y's, and then the number of equations is n. So one of the attempted response is to just write down here, write down r plus s, bigger than n. All right. Now this turns out to be wrong. If you give this response, then that is not the correct response. With this condition, there's no guarantee that my system of equations can have non-trivial solutions. This simply is not a valid guarantee. And the situation becomes then complicated. What's the reason of the complication? The reason was already contained in the answer to this complication is already contained in Alejandro's title, Dos Dimensiones son muchas. Now my equations on the left-hand side are of degree 2, are x, y times yj. 2 dimensions, so already a lot. It was quite a bit of difficulties. Let me just invite you to maybe contemplate it. One case here. How about this one? Let me say I put down this condition. The number of variables r plus s totally equal to 8, and then there are 7 equations. So now the number of variables exceed the number of equations by 1, not just by 1. And then, in other words, I would like to introduce this simplified system, r x's, 8 minus r unknowns, and 7 equations. Would there always be a non-trivial solution to such systems? So that's the question to contemplate as we go on with the talk. Let me now get into Sam Gitler's original and novel approach to this problem. And that is done in his paper, The Projective Stiefel Manifolds Part 2. And this is the way Sam attacked this problem. So imagine that you have that system of equations given in my page 2. And now you pick some values for the x variables, make sure that not all of them are 0, and plug into the system. So that the x values now get absorbed into the coefficients, and the system now becomes just a linear system of the y's. It can be rewritten in matrix form like that, and that is another star with the s indicating that they are y unknowns, y variables. Okay, now focus on those systems that admit trivial solutions only. All right, then this system star would have only trivial solutions, and we have a terminology to describe that kind of coefficient matrix. That coefficient matrix, the big one that you see up there, has linearly independent columns. Right. So for any x vector you pick, substitute into the equation, get the coefficient matrix A of x, and that has linearly independent columns. There is a term for the collection of all such matrices. They are called Stiefel manifolds. Up to the sense of homotopy, this term coincides with the classical use. Let me not bother to explain there. That is called the Stiefel manifolds. The notation for Stiefel manifolds is Vs of Rn. This is a matrix of S columns and N rows. The vertical columns are n-dimensional vectors, and there are S of them. All right. Okay, so that is the concept of Stiefel manifold, part of the title. And then you have this, you focus on those that will cause the system to be only trivially solvable. And with that we summarize the process above like this, that we take the x, we get the coefficient, and then there's a mapping from the truncated Euclidean space to the Stiefel manifold. And you notice that if C is any non-zero real number, then f of C of x is equal to C times A of x. That simply is because if you take the original system of equations and you multiply the left and right hand side by C, it basically is the same equation. All right. So that means that we are entitled to do the following. We make some identifications. If on the left side here, we identify any vector x with C times x, C is a non-zero constant, and view the two identified things as the one object. And on the right-hand side, we take those matrices with column independence, and we also do the same identification. We identify any matrix A with C times A. Many speakers before me had talked about identifications. That is a very common procedure in mathematics, and for good reason. Mathematicians do identification for the purpose. Let me try for people who are not used to this kind of identification. Let me try to illustrate with a daily life example. I have a Canadian coin here, $2 Canadian coin. I have a peso bill here, $20 peso. All right, they are obviously different objects, like the X and the CX, but exchange rate being 1 to 10 nowadays between Canadian and Mexican currency, 10 times this is going to cost the same as 20. So the exchange rate being 1 and 10. So there's every reason to identify these two as one object. And then the identified object will carry some essence. And that essence is like the perspectivity given by the previous talk. The essence is perspectivity in the previous talk. In my case, this identification brings out the essence of purchasing power. All right. This guy and this guy, if 1 times 10 is identified with that, then together this identified object represents the abstract notion of purchasing power. So we do this kind of identifications in order to bring out the essence of the whole mathematics. Now, on the right-hand side, when identification is made, we take matrices which are column independent. We identify the matrix with any constant multiple of it. And what results then, the identified object will constitute the projective Stiefel manifold. It is now denoted by the Stiefel manifold's notation with a P in front of it, signifying projectiveness. So we'll summarize the situation here. Remember that I take the x values and form the Stiefel manifold, then I do identification. The vectors identified in that way was also the subject of the previous talk. We get to the real projective space. The Stiefel manifolds identified in the way I described, which get to the projective Stiefel manifold. Everything involves multiplied by a constant, so this clearly is a commutative diagram. All right. So in our analysis of the equation problem, we come to a commutative diagram. Whenever a commutative diagram appears with some maps between various geometric objects, algebraic topology enters. For example, we can bring in the fundamental group. The top guys have trivial fundamental groups, not interesting, but these two bottom guys have fundamental groups that are very interesting. And they are simple and interesting. The fundamental groups for real projective space and the projective Stiefel manifold, apart from some negligible cases, they are both the group of order 2. And in fact, the map here between them make a correspondence between the fundamental groups, and this correspondence, thanks to this commutativity of the diagram, is a one-to-one surjective-bijective correspondence. So that is very simple. Fundamental groups will bring me into algebraic topology, but algebraic topology can do some more. We'll not only let fundamental group enter, we'll let the cohomology enter. In other words, for all these geometric objects, especially these bottom two, I'll take their cohomology ring. So for the projective Stiefel manifold, I take X star, its cohomology ring. Same for the real projective space. Now the original map that goes from left to right in cohomology induces a homomorphism of rings from right back to left. That is called PF star. For example, it will take some element U here, some cohomology class, and you will bring it back to some cohomology class V. And this is a ring homomorphism. And it's indicated by going the opposite direction. All right, so this now brings me into algebraic topology. And let's see what kind of general situation is in algebraic topology. Whenever you have some manifold X, let's say, and then you look at its cohomology ring, and you construct the cohomology ring from X. That is, as Professor Bill Browder says, it takes 40 hours to describe. This is a construction is rather hard to describe. However, we are very lucky. Inside the cohomology ring, it always contains a so-called one-dimensional part. The cohomology ring contains a subportion which we call the one-dimensional cohomology, one-dimensional part, denoted by the X with the upper subscript 1. So it is very easy to describe. How do you describe it? We just describe it as the set of all homomorphisms from the fundamental group to the group of two elements. I'm taking cohomology with Z1 to Z coefficients. So take the fundamental group and look at all homomorphisms from the fundamental group to the coefficients you take. The various homomorphisms then correspond in one-to-one manner to the various elements in the one-dimensional part of the cohomology. Our spaces are very simple. Our spaces only have fundamental group equal to 2 elements. So this homomorphism set is very simple. In fact, in each homomorphism set, there's only one non-trivial element here, a U over there and a V over there. They are one-dimensional cohomology classes, and they correspond under the PF star. So we are up to here under the induced mapping cohomology, the one-dimensional cohomology element U and the one-dimensional non-trivial cohomology element V in these two respective places correspond. Now, in ring theory, whenever you have a homomorphism of rings, when two elements U and V correspond, their powers will also correspond. So the powers of U are here, U square, U cubed is U squared multiplied by U again, and there's a bunch of powers for the U's over on this side. And the V's also have powers on that side. Since the U and V correspond, their powers also always correspond one by one, and that is now the situation. Now, we'll do some algebra. Any element U in any ring would have a height. What do I mean by the height? A height, I call it H, which is a power such that when you raise U to the X power, you get a zero ring element. And such that one previous power, U to the X minus 1, is not zero here. So you keep raising this potential element in question to powers until the first time you find the power to be zero. If you never find it to be zero, you say that the height is infinite. But usually you will have a finite height for manifolds, and when you get to this height, you call it H. Okay, now since the powers of U squared, U cubed, U4 are corresponding to respectively V squared, V cubed, V4, we draw now a very common sense conclusion. This correspondence between U and V, the height of V cannot exceed the height of U. Because when you go over these elements, U squared, U cubed, and so on, when you get to zero, the corresponding V element will also get to zero. So the height of V would be occur earlier. If not, it can never be occur later. So that is the conclusion. This one is the conclusion of our analysis. To summarize, what we did is that we have started with the system in question, a homogeneous bilinear system with those parameters R, S, and N. And we focus on those that has only trivial solutions and no others. We focus, we analyze it, we bring in the concept of projective Stiefel manifolds, we let algebraic topology enter, and then we find that there must be U and V, these one-dimensional cohomology classes, and the height of V cannot exceed the height of U. That is the summary. Now, I'll go back to the response. The response to my imitation is to deliberately write it otherwise. the height of V exceeds the height of U. So put that down as a response. The height of the projected phase is clearly very well known to be R. So we put down this response. R be bigger than the height of U. Alright. So this is the response that we shall put down. If we put down this response, we know that we will be a correct response. Because if the original system has no non-trivial solutions, then according to our analysis, the height of V should be smaller than or less equal to the height of U. If I put this to be like that, just in the opposite way, then I arrive at a contradiction if I assume my system to be non-solvable in the non-trivial sense. So if I have this condition, to say that the system is non-solvable would be a contradiction. So this is the correct correspondence. The correspondence already include the R, and then indeed the height of this element U as a one-dimensional cohomology element in the projective Stiefel manifold, it has been explicitly computed jointly by Gitler and Handel in a paper slightly earlier than the previous. And this given as a numerical function of S and N. The Stiefel manifold is Vsn, so that height of its cohomology part certainly would be a numerical function on S and N. And in the earlier paper, that height has already been computed. Okay, this is not yet Sam's answer to the challenge. The challenge is to get a response. This is the response, but unfortunately, it turned out that this response, which I repeat here, the R is exceeding the height of that element U, which I call the Gitler-Handel function, depending on S and N. Putting down here as a numerical condition is correct, and it works, but unfortunately, this numerical criterion happened to coincide with an earlier result of Stiefel. And this is the paper by Stiefel, occurring much earlier. And Stiefel, in his older paper in German, also reached at the same numerical condition. So up to this point, we cannot say that Sam has given up his original research. But Sam certainly has a novel field. In other words, Sam did not stop here. That is not his final page. And in fact, he only started here. And then the remaining story is like this. Sam, who is the Norman Sinrod's PhD student, and Sinrod in the 1950s had a great contribution by recognizing that in any cohomology regular X star of it, there are certain relations between elements beyond the relation of one element being a power of another. For example, W equal to Z to the cube, then W and Z are related by that relation. W being the cube power of Z. Sinrod's great contribution was to show that other relations, called Sinrod reduced power relations, also hold in the cohomology ring. Sinrod reduced power relations are something like this, that the element W is related to the element Z by writing W equal to square K of Z. And we read it as W is the K Sinrod reduced power of Z. So that is, of course, something that everybody in Princeton learned when they were graduate students around that time. Around that time, Sam was one of those students, Jose Adam also, and so on. So what Sam really did in his paper, which I quoted in the beginning, was that he gave a thorough analysis of the Sinrod reduced power relations. Not just the power relations, Z equal to WQ, but this new relationship of Sinrod reduced power. Sam examined that, scrutinized that very carefully. And this is the whole admirable technical point of Sam's paper. Sam's paper had two very penetrating technical points, which I have no time to present to you. One is his decision with Handel on exactly the Gitler-Handel height function, so that he can write it down in the box. And the other is that he explored this new relationship of Sinrod reduced K powers, and then he managed to find out an improved response. Sam's original response is not the top one here, but it's this one here. He writes down a numerical condition involving these parameters R, S, and N, and this condition that Sam writes down is less restrictive and less stringent than those of Stiefel. In other words, this is a set of better numerical conditions than the above. And this one that is not so restricted, therefore it's more applicable, but it still is correct and true. And then this stringent condition will also guarantee that the system of homogeneous bilinear equations. So under this kind of numerical condition, we guarantee to admit non-trivial solutions. This is Sam's main theorem in this paper. All right. This numerical condition can be found in the paper, involves some binomial coefficient, which is slightly technically described. Allow me not to give it in full to you here, but let me give you one example. All right. For example, specializing from some of the cases, this is one of Sam's improved conditions. R, the number, numerically the number of x variables, is equal to 2 to the power of 3. And S, the number of y unknowns, is equal to 2 to the same power plus 2. And then R plus S minus N be bigger than or equal to 5. This is one of the conditions copied out from Sam's paper. I simplified it a little bit. This particular case might also occur in other places, but this is a valid condition. If I have a system of homogeneous bilinear equations, altogether n of them, and if the number of x variables is 2 to some power plus 3, the number of y variables is 2 to the same power plus 2, and I have this numerical inequality, then I guarantee you, I don't care what the coefficients are in that system. Some of the coefficients may be blurred, may be blocked by milk, may be blurred by coffee, and some of them they may be subject to numerical inaccuracies, errors, because of computer output. I don't care. But those systems under these numerical conditions are guaranteed to have at least one non-trivial solution. One of the even simpler cases is when t is equal to 4. So 19 x variables, 18 y variables, and 32 equations. All right. At this point, we may go back, all right, and see a little bit better of how the situation is. Look at this condition, that R plus S minus N be bigger than or equal to 5. R plus S is your total number of unknowns. N is your total number of equations. We still get back to what we talked about 20 minutes ago about the linear case. We want the number of unknowns exceed the number of equations so that we have some extra degrees of freedom. Now, in the case of homogeneous bilinear case, we really learned something. To just require that the number of unknowns exceed the number of equations is not quite enough, as I showed you before, as I mentioned before. But if you guarantee that the number of unknowns exceed the number of equations by at least 5 units, then under this kind of value for R and S, you shall be guaranteed a non-trivial solution. And one of these cases is like that. So that is this is one of the 7 theorems that these ones will guarantee a solution. And as I commented before, it is already quite a masterful piece of work because of the clarity of the concepts and the cleverness and the skillful use of technical things like spectral sequences mentioned earlier that allows these numerical conditions to be obtained and get at least some response to the original question, which is still open up to this day. Now, then one must also mention that what if I go to Stiefel's old paper and pretend that Stiefel also knew C0 and apply the C0 reduced case power? What if I do that? And here is the wonderful thing. It turns out that even if anybody goes back to Stiefel's paper and in the paper pump in the additional ingredient of C0 reduced powers, there will be no improvement. C0's paper cannot be improved by the use of C0 reduced state powers. But Sam's approach, through the use of this geometric object of projective Stiefel manifolds, does allow the improvement of bringing in the new truth of C0 reduced state powers and therefore get some real answer to the unsolved problem. Let me now conclude with this case. All right, as I mentioned before, this is still an open problem. In what sense is this open? It is like this, There are many, in fact, many mathematicians work on this problem, although sometimes under quite different format. Some would emphasize the geometry, some would emphasize spectra, whatever. Many work on this problem, and they get some numerical conditions to put in the blank box, right? All of them are true, all of them are interesting. However, at least for many of them, they can not answer the following question. Somebody will come up to them and say, hey, your numerical conditions are very nice, but are those the best you can offer? Would there be some clever person, clever graduate student someday who will come forth with a set of less restrictive conditions that will less restrictive than yours, that will also guarantee that the system with these parameters shall be non-trivially solvable? Most people who have contributed to this cannot answer this question in complete satisfaction. There might still be for the group for it. For example, this one. All right. And for the time since Sam's publication of his paper up to a few days ago, that problem cannot be answered. We don't know whether Sam's numerical condition in this special case will be the unimprovable one. All right. All right. Now, coming down to Mexico and preparing for this talk, I happened to hit upon this very minute proposition. I said that this condition, the Sam has 19, 18, 18. I will cut down the R by 1, 18, 18, and 32. Then, what I am saying, this condition, one less strengthened than Sam, will not guarantee non-trivial solutions to an arbitrary homogeneous system with 18 x variables, 18 y variables, and totally 32 equations. In other words, counterexamples exist. I was able to construct a counterexample on September the 16th, just preparing to begin my trip to Mexico. And that happens to be Mexico's National Day, September the 16th. And so I can tell Sam now, if I have a chance, maybe sometime in the future, I'll tell him that, Sam, your conditions are already unimprovable. If anybody tries to improve it by 1 unit, he will fail. He will give something false. And with this, I dedicate this little tiny result to Sam in memory of his inspiration, in memory of his friendship, and in memory of his humanity. Thank you very much.
¿Algunas preguntas para el doctor Lam? Jesús.
Sam's paper that you referred to, the one from 1968, is stated in terms of inversions. I believe not in terms of his writing equation. So thus the question is that true? Well, but that's not. So if that's true, your recently proved optimality result has implication in terms of the immersion?
Well, I can only speak for this particular case.
Yes,
in fact,
in that case.
there is some little subtle difference. If you have some inversion, you might want to say that it is possible to inverse, but there is a slightly more profound question, whether you can write down a non-singular bilinear map to realize the inverse. You may write down a non-singular by skew, but in reality, it's a subtle issue in all these methods. The counterexample I managed to construct a few days ago is a bilinear example. It involves the feature of linearity and bilinearity. So it's a little bit more subtle than the question that you referred to.
The answer is that it does not have an implication in terms of
I don't know whether, knowing that it's linearly impossible, whether that will affect your command to the robots, that they should study more than linear algebra. That I don't know. But in my perspective, the use of non-singular bilinear maps is the one that is easiest to appeal to enlist more undergraduate or graduate students into this area of research that is still open. However, it's difficult because there are already giants standing before us, right? We can only pick through their armpits and try to see if we can get them something more, right? But it doesn't mean that we should not do it. Giants are giants, and we one day will become bigger giants. So there is still a lot of opening things that maybe some younger further graduate students can have new perspective. And indeed, there is quite possible new perspective. And I will mention my name just to stimulate everybody's thinking. Remember that cohomology ring, the cohomology ring that comes in, outbreak topology edges. All right. So one direction to think about, very primitive, is whether you can use, once you're in linear algebra, all right, then you can contemplate using motivic cohomology. And that really is something open to the future young. I hope that I can live to further day to see a fresh results coming out from this direction of motivic cohomology.
Any other questions? ¿Alguna otra pregunta? Agradecemos de la conferencia del doctor Kee Yuen.